We're going to do the state equation formulation mechanical system example from the top because we had a fire alarm happen in the middle and audio wasn't recording and all of that, so I think it's best if we just start over. So, look to zoom in. Alright, so the problem is a mechanical translational system. It has two masses, two springs, two dampers, and there is a velocity source input. So this node down here is not connected to ground, it's movable, and there's a velocity that's prescribed by some broader scenario. Likely you have terrain, and this is maybe a model of a vehicle with a person sitting on it or something of that nature. Let's see. Notes. There we are. So let's first define the positive velocity coordinate arrow. So let's draw in that direction. And so that's our positive velocity. And we're going to go ahead and draw a linear graph and find the normal tree first. So this system has 1, 2, 3, and the fourth is ground, distinct velocities. So we'll draw in ground first and 3 non-ground distinct velocities. So those are those nodes. Let's connect the velocity source here. Since the velocity source is in the direction of the coordinate arrow, we can look back at our rules for sign convention and discover that that means we have to draw our arrow toward ground, Vs. These other two nodes are the mass nodes, so we always draw mass nodes to ground, so let's do that. So this is M1 and M2. Now, there are a spring and a damper that connect this node, the velocity input node, to the mass 1 node by these two connections here. So let's draw them in. So we'll say this one's K1 and this one is B1. The direction of the arrow from our convention is that we draw the arrow in the direction of positive velocity. So positive velocity is drawn from the source velocity to mass 1. So we can draw our arrows like that. And similarly, we can do the same thing with the connection between mass 1 and mass 2 going through K2 and B2 in parallel. I really like talking to you guys live better. This is kind of sad. Okay, so we have our linear graph. That's the description of this schematic mechanical system. And our normal tree construction can be executed by going down our list of elements to select for the normal tree in descending order of priority. So top priority is to select as many as possible across variable sources. So there is that across variable source. There's only one in our graph. Remember our two rules that we can never violate. The first rule is we can't create a loop in the normal tree, and the second is that we have to select as many as possible elements for the normal tree without creating a loop. So Our next, so there are more that are possible without creating a loop, so we need to continue. Our next priority is A-type energy storage elements, which for a linear translational system, or a translational system, I should say, are the masses. So mass 1 and mass 2. And we have damper, and spring that if we chose any of these elements, it would create a loop. So we know we're done. Otherwise, we would have gone on to D-type, which would have been B1 and B2, and then finally T-type. Okay. So now we can define our primary variables to be across variables of the elements in the normal tree and through variables on links. So Vs is in the normal tree, Vm1, Vm2, Fk1, Fk2, Fb1, Fb2, and that's it. Secondary variables, we just permute this, so Is, sorry, not I, it's not a current, it's a force, right? Force from the source, the force on mass 1, the force on mass 2, the velocity across K1, the velocity across K2, velocity across B1, and the velocity across B2. Okay. Our state variables are always going to be the across variables on A-type elements in the normal tree. Those are the first set of them. So we have two A-type elements in the normal tree. So the across variables are our state variables, Vm1 and Vm2. And then our state variables also include through variables on links, which are the elements that are not in our normal tree. So through variables on T-type energy storage elements in the links, not just any element in the links. So T-type are the two springs in this case. So we have Fk1 and Fk2. So the system order can be determined by just counting the number of state variables. So n is equal to 4. In this case, there are 4 state variables, and we are ready to go with our elemental equations. So I guess before we move on, it would be good for us to write our state vector, which we can do at this point because we know our state variables. Remember when we say state vector, we really mean the vector valued function x. Okay, so it's Vm1, Vm2, Fk1, and Fk2. And we could choose any order for those. I chose this order when I did it, when I wrote my notes, so we're going to choose that order for this case, but any order is acceptable as long as you are consistent with your definition of x. Okay, so our elemental equations, remember the method I like to use is to identify all of the passive elements, the non-source elements in the linear graph, and list them in a column and then write the associated elemental equation next to it. So let's do that. Let's make a column M1, M2, K1, K2, B1, B2. And the elemental equation for a mass is just Newton's law. So dVm1 dt equals 1 over m times Fm1. Should have had a 1 subscript there. So there's that elemental equation. I'm going to write this one, dvm2 dt equals 1 over m2 fm2. And for spring elements, it's Hooke's law, the derivative of Hooke's law, time derivative. So it is dfk1 dt equals, so it's F equals kx, that's Hooke's law, right, where x is the displacement across the spring and F is the force through the spring. dfk1 dt is then going to be equal to, with k1 being a constant, k1 dvk1, or sorry, not dvk1. It's dx k1 dt, which is just vk1. Okay? All right. Good. So let's also write fk2 dt. It's essentially the same equation with k2 in it and vk2. For a damper, linear damper, we have that the force is proportional to the velocity. So we have fb1 equals b1 times vb1. And fb2 equals b2 vb2. Okay. And all of these are solved for the primary variable on the left-hand side. So vm1, primary variable, vm2, primary variable, fk1, fk2, fb1, fb2. So if they were not, we would then solve each of these so that the left-hand side had the primary, and all of our secondary variables were on the right-hand side. So it's already like that, so we don't need to do anything. Okay. Continuity equations. We need, so I'm going to copy this graph down so that we can see it while I do this part. It's kind of hard to flip back and forth on this. So, okay. So we need continuity equations, remember, are determined by our contours. So we need to draw some contours. And remember that our contours have to intersect one and only one passive branch of the normal tree. Okay, so I'll do it in orange. So this would be a case, and so would this. Those are two good cases. There's no need to do anything fancy here, although we could do other contours. The equations should come out the same. The first equation we'll use this contour for. It says that, so the way that my trick here, or it's not really a trick, we need to solve for the through variable that goes through the only normal tree branch that we've cut. Okay, that's always what we need from our continuity equation. That's what we're going to solve for. So what I typically do is I write that variable and I say equals and then whatever it equals. So fm1 equals, so that's the through variable through this branch, equals fk1 plus fb1 minus fk2 minus fb2. So fk1 plus fb1 minus fk2 minus fb2. Okay. We could have also, of course, just added up all of the forces going into this node and set that equal to 0 and solve for fm1, but we just sort of skipped a step there, and it was a little bit cleaner this way. So let's do the same with fm2. fm2 equals fk2 plus fb2. fk2 plus fb2. All right. So that is all we need we only needed 2. We could do that by using that formula that I've listed here, or we could just draw, or we would just count the number of passive branches that are in the normal tree. That's also equal to 2. Always equal to the number of continuity equations that you need. Okay, so compatibility equations, we're going to need 4 based on our formula for the number that we need. But once again, all we needed to do is count the number of links that we have, the number of elements that are not in the normal tree. So if K1, B1, K2, B2, so we need to write a compatibility equation for which we solve for the across variable across the link that we include into the normal tree to form a loop. So compatibility equation is just like KVL, right? And the continuity equation is just like KCL, Kirchhoff's 2 laws. And the compatibility equation, in this case, for K1 is going to be a loop that's created. We have to sum all of the across variables around a loop, so they're velocities in this case. All the velocities around a loop, and it must be equal to 0, of course. Now, once again, we know where we're going. We want to solve for VK1. So the way that I typically do this is to treat this just like a vector, which it is in some ways a vector, and see what the addition would be in order to get there with the other branches that are in the loop. So we write VK1, which is what we want to solve for this formula, is equal to, so we put this into this loop. So VK1 goes from this node to this node. So we need to see how we get from this node to this node using the other path. The other path is VS, and the arrow is in this direction, so we just use positive VS. And then we have to go against the arrow to this second node, so VM1, so minus VM1. So if it's in the direction of the arrow, it's plus. If it's against, it's minus. And it's already solved for the variable we need. So that's the nice little shortcut. Okay, so we can also write the VK2. We could place that one. So VK2 is equal to, so it goes from this node to this node, and the path that gets there along this other path is VM1 minus VM2. Okay, and very similarly with the dampers as well. So VB1 is equal to VS minus VM1, and VB2 is equal to VM1 minus VM2. Okay, because it's like the same loop that gets created, right? Alright, so our compatibility and continuity equations are now found. So we have all of the equations that we need to solve this. So now we just need to do the algebra. I'm going to rewrite these in a column once again. So we have M1, M2, K1, K2, B1, B2, and what we're going to do is we're going to plug in the continuity and compatibility equations into our elemental equations to eliminate all of the secondary variables. That's our first step. So our elemental equations say Vm1 dVm1 dt is equal to 1 over m1 fm1. So we have a continuity equation by construction. Always we're going to have a compatibility or continuity equation for that, and here's what it's equal to. So we can say dVm1 dt is equal to 1 over m1 times, and then it's this long expression, right? fk1 plus fb1 minus fk2 minus fb2. Okay, so we're going to leave this alone now. We might be tempted to just keep plugging into this, but trust me, we want to continue with our process. It's going to end up better for us if we do. So dvm2 dt is equal to 1 over m2 times fm2, right? And there's, of course, another continuity equation for fm2. It says that it's just equal to fk2 plus fb2. So fk2 plus fb2. All right. Now we have our elemental equation for the spring 1, k1. So df k1 dt equals k1 v k1. So df k1 dt is equal to k1 times vk1. But we have a compatibility equation for vk1, which is just vs minus vm1. Okay, for k2, it's a very similar equation. So we have df k2 dt equals k2 times vk2, but we have an equation for that says that vk2 is equal to vm1 minus vm2. Okay. All right. So finally, for our damper equations, we had that fb1 was equal to b1 times vb1. That was the elemental equation from above. So vb1, we also have a compatibility equation for that, vs minus vm1, and it's very similar for the second damper equation. So this one, vb2 is equal to vm1 minus vm2. Okay. So at this point, we have eliminated all of the secondary variables. We have a fourth order system, so we're looking for 4 differential equations to end up with. So these 2 are algebraic equations, they're the extra ones, but they're solved for the primary variables, fb1 and fb2, that we need to insert into these equations above in order to eliminate non-state and input variables. The 4 differential equations that we should end up with should all be in terms of state variables and input variables, okay, and derivatives thereof. All right. So the next step of our algebra is to, I'll just sort of write a little note here, insert into these. Okay, I'll make the brace a little bit bigger. So take these, insert them into those to eliminate those final 2 primary variables that are not state variables. If you look through here, vm1, state variable. fk1, state variable. fb1 is one of the primary variables we need to eliminate. fk2, state variable. fb2 is once again one of the primary variables we need to eliminate. If you check the rest of these equations, you're going to find exactly the same thing. They're either state variables, inputs, or fb1 and fb2, which we can now get rid of. So we can rewrite these equations. So let's repeat our column here. It's only going to go down to k2 in this case, but we can repeat up to that point. You guys wish you could do that. I know, it's pretty cool. So dvm1 dt is equal to 1 over m1 times fk1 is a state variable, we don't need to eliminate that, plus fb1, which is b1 vs minus bm1 from this equation here, right? Plus fk2, which is a state variable. Sorry, that was minus. You guys aren't here to help me when I make mistakes. Alright, so minus fk2, which is a state variable, minus fb2, which is given by this expression, b2 vm1 minus vm2, and we have another parenthesis to close. Alright, so that is our state equation for this first row. So for m2, we have dvm2 dt equals 1 over m2 times fk2 plus fb2. Now fk2 is a state variable, plus fb2, which I forgot to check, we did use this equation here, but we're going to use it again. b2 vm1 minus vm2. Now, let's inspect. We have fk2 is a state variable, vm1 state variable, vm2 state variable. You might say, what about b2? What about m2? Those are parameters, and so those are, although we haven't specified a specific value for them, we've treated them as constants, and for a given problem, we know what that mass is, or what that damping coefficient is. Okay. Now, we have our fk1 dt, so dfk1 dt is equal to k1 times vs minus vm, right? vm1. Now, vs is an input, more like a u. Vs minus vm1 is a state variable, so we don't have to do anything to this, we just rewrote it. And fk2 is equal to k2, and we've got vm1 minus vm2. Well, those were already state variables, so we don't need to do anything to that one either. So we're good. We are done. Now, to write it in standard form, which we always like to do, standard form, you might just think this is a useless exercise, but it's actually a very useful form. So I've talked a little bit about it before, but it's going to be a form that we're going to use a lot, and you'll see more about why soon. So standard form is going to be that dx dt is equal to, so this is our state vector valued function, right? It's going to be equal to ax plus bu, right? Always equal to ax plus bu. We just need to specify what the A matrix is. So I just draw a big empty matrix. And then x, I actually like to write in x again. We said that x was vm1, vm2, fk1, fk2. We said that. I'll scroll up so that you can recall where we did that. We did that up here. We defined our state vector, or our state vector valued function, right? So this is our A matrix, A, which has to be a 4 by 4 matrix, because we have this side of the equation is a 4 by 1 vector, column vector. This side has some sort of matrix times a 4 by 1 gives you a 4 by 1. The inner dimensions collapse, and so this and this collapse, and we get a 4 by 1 vector coming out, which would be better. And finally, our B matrix is going to be a 4 by 1 because our single input in this system is the velocity source, right? So this is B, it's a 4 by 1. This is a 1 by 1. This is our U, right? Probably should have U, which is a 1 by 1. So these inner dimensions collapse and we get a 4 by 1 out. Which would be better if we're going to add it to another vector, right? I probably should have made this a subscript too. So X. So 4 by 1. Okay, so now we just need to fill in what A and B are. From here, we just need to read off. So this first element is going to multiply VM1. So we need to find the coefficient of VM1. Now VM1 shows up twice in this, so we probably should have written equals and brought those together, but we can do this in one fell swoop if we're very careful. So VM1, all of these things are going to have coefficient of 1 over M1, right? Moreover, we have both of these, so this is going to have a negative sign, and this one's going to have a negative sign, okay? So we've got a negative 1 over M1, so maybe let's even do that, negative 1 over M1 times, and then we've got B1, that's here, and then we've got B2, that's here. So they're added together, B1 plus B2. Okay. All right. Now our next term is VM2 term. So we scan this equation, we see VM2. There it is. There's only one of them. So we've got a 1 over M1, a negative sign and another negative sign. It's positive, so it's B2 over M1. And FK1 shows up in this first equation as well. FK1 has the coefficient of 1 over M1. And FK2 has negative 1 over M1. Okay? All right. We have one more thing to do in this first equation, though, to write it into this standard form. That is, we have a VS term. And the VS is described by the B matrix. The way that VS enters into this equation is described by the B matrix. And the B matrix here, we only need to pick just one for this equation, one element for this equation, and that is whatever the coefficient of VS is. In this case, it's B1 over M1. B1 over M1. Okay? Now, the second equation, so the first one was the longest, so the rest of them should be a little bit better. Do we have a VM1 here? We do, VM1. So B2 over M2 is the coefficient. B2 over M2. And the coefficient of VM2 is negative B2 over M2. All right. And FK1 doesn't show up, so we have a 0. And then FK2 shows up as a 1 over M2. We have no input in this equation, so a 0 goes in that row of the B matrix. Okay. Now we have FK1, so we come to this equation here. We need to transcribe it into this row. So dfk1 dt, which is on the left-hand side, equals k1 vs minus k1 vm1. So ignore my emails that pop up. Okay, so we've got vm1, which is our first state variable. So we have negative k1 vm1, 0 vm2, 0 fk1, and 1 over m2 fk2. Oh wait, no we don't. I just read it from up there. There's no fk2 in this formula, or in this equation, so 0. And Vs is going to appear through k1. That's its coefficient. Okay, so last equation now. Vm1 has a k2. Vm2 has a negative k2. And then there are no forces in here, and that's equal to, there's no Vs in there, so that is our those are our A and B matrices. So then we're done with the state equation. So the state equation is this. Our standard form output equation we can write. So we asked at the beginning, when I ask you for the output equation, you need to know what the outputs are. And in the problem, I stated that outputs are the spring forces and linear momenta of the masses. Okay? So what we need to write is, so the forces on the masses, we need to write an equation for each of these outputs. The forces on the masses are, so I'm going to write it not in standard form first. Forces on the masses, we already have equations for them, right? So Fk1 is a state variable. So you have to be able to write each of your outputs in terms of state variable. So Y1, our first output, is Fk1, which is already a state variable, so we're good to go there. Y2 is going to be equal to the other spring force, which is also a state variable. Great. Now I asked for, I'll say Y3, I asked for the linear momenta of the masses. Now that's very closely related to the velocity of the masses. It's just the mass of each mass of each mass times its velocity. So m1 vm1, and our last output is going to be m2 vm2, which is the momentum of mass 2. So now we just need to write that in standard form. It's really easy, so you have to write it in terms of state variables. So each output needs to be in terms of state variables and input variables to work in our standard form. We have that. It was easy to do, and it often is. So this is going to be our C matrix times x. So output is always Cx plus du. So our x is once again Vm1, Vm2, Fk1, Fk2, plus, and then once again we're going to have a 4 by 1 D matrix times Vs. Okay? So Y1, so that's our first one. If we were going to write this out element-wise, we would say Y1, Y2, to Y3, Y4. So we have to write it in terms of this matrix vector product and then sum. So let's see, this first one, Y1, is Fk1. That is the third of our state variables. So we have 0 Vm1 plus 0 Vm2 plus 1 Fk1 plus 0 Fk2. Similarly, Y2, this row, and there was also no input as well. Y2 is equal to 0 Vm1, 0 Vm2, 0 Fk1, so Fk1, so this is the equation we're transcribing, and 1 F2, because this is equal to Fk2, 1 Fk2. And then there's no input in that equation either. So Y3 now is this row. So here's our Y3 equation. M1 times VM1. So we have M1 times VM1, and then nothing else, right? Similarly with Y4, 0 VM1, but M2 times VM2, 0, 0, and 0. And so now we have our C matrix, which has to be a 4 by 4, because it has to come out with 4 outputs, multiplying in a state vector value function. That's a 4 by 1. Our D matrix is a 4 by 1, multiplying a 1 by 1 input vector, which is a 1 by 1. A 1 by 1 input vector. Okay, so that is how to do the entire thing. There's nothing else to do. So now we'll learn different techniques of what to do with this state and output equation formulation in the coming weeks. But we're just sort of learning still how to do this part. So yeah, I hope that you guys are enjoying this from wherever you are with your Halloween candy and costumes. So maybe you're not going to watch this anytime soon because it's Halloween tomorrow. Anyways, enjoy this when you get to it, and I'll see you tomorrow in class.